Welcome to the deep dive. Today we're tackling a really interesting puzzle in making large language models smarter. It's about how we get them to reason effectively, especially when they hit a snag.
Exactly. That moment where a person might stop, think, hang on, that doesn't seem right, and, try a different angle. That
That
reflection,
reflective behavior, yeah, it seems crucial.
it absolutely is. LLMs are getting really good, especially with things like chain of thought reasoning, breaking down problems step by step.
And we're using reinforcement learning, RL, to fine-tune them, to make those reasoning paths better.
Right. But here's the catch. Sometimes these models look like they're reflecting, backtracking, fixing errors, but it's not always clear if the standard RL training methods are actually teaching them to do this reliably, especially when they face a new problem at test time.
So is it a genuinely learned skill for new situations, or just sort of a lucky byproduct of the training process?
That's the question. And how do you build that capability in a principled way?
Okay, and that leads us to the source material for today, a recent research paper tackling exactly this. It's from researchers at Northwestern University, Google DeepMind, and Google, titled Beyond Markovian: Reflective Exploration via Bayes Adaptive RL for LLM Reasoning.
Yeah, and their core argument is, well, pretty compelling. They argue that conventional RL, what we usually call Markovian RL, has some fundamental limitations. Limitations when it comes to really explaining or encouraging this kind of dynamic reflective thinking when the model needs it most during actual use at test time.
And they don't just win out the problem, they propose a solution, right, based on a different approach to RL.
Exactly. They use Bayes Adaptive RL. It's a different framework, and they've built an algorithm from it they call BARL.
BARL. Okay, so our mission for this deep dive is to really get into what this paper tells us. Make LLMs better reasoners.
We want to unpack why the standard approach, Markovian RL, might fall short here.
Understand how their BARL algorithm offers a more structured way to get this helpful adaptive reflection.
And maybe the most interesting part, when should an LLM actually reflect? What does Barwell tell us about that?
Getting a clear view of the academic innovation here. All right, let's jump right into the problem then. Why isn't standard Markovian RL quite cutting it for this test time reflection we want?
Well, a source points out that even if you sometimes see behavior that looks like reflection, with standard RL, there's no guarantee it's an intended result of the training objective, especially for test time adaptation. The theoretical underpinnings aren't really there for that specific behavior.
And they trace this back to some core ideas in standard RL, like the exploration versus exploitation trade-off.
Precisely. In standard Markovian RL, that balance trying new things versus sticking with what works that's mostly sorted out during training. The agent explores, learns the best paths, but then once it's trained, the idea is usually just pure exploitation.
Just follow the single best strategy it learned.
Right. There's no inherent reason built into the framework for it to keep exploring or gathering more info once it's performing the task for real.
So at test time, it's just executing the learned program, not really supposed to be exploring other options.
That's the standard view, and that connects directly to the Markov assumption.
Ah, right. The idea that the current state tells you everything you need to know.
Exactly. Standard RL policies base their decisions only on the current state. They assume all the necessary information is right there in that snapshot. They don't inherently need or typically use the full history, the sequence of steps, actions, intermediate results to adapt their strategy on the fly.
Okay, so unless the history is somehow encoded into the current state definition, the policy doesn't really look back further to decide what to do next.
Generally, no. And if your decision making is purely state-based and you've learned the best action from that state during training, well, there's no built-in signal telling you to second guess or deviate.
Which means no real mechanism pushing for that test time adaptation or reflection we're talking about. Why backtrack if the policy just says do this now?
Exactly. And the source makes a pretty strong point that this can actually lead models towards just memorizing stuff.
Memorizing successful sequences from training rather than truly reasoning.
Yes, that's a critical argument they make. They suggest Markovian RL can find optimate policies simply by remembering the action sequences that happen to work during training, trial, and error. They even have an experiment supporting this. They trained a standard RL model with length constraints. It learned to just spit out a short, non-reflective answer quickly during training.
Like it memorized the answer format?
Kind of, yeah. And then when tested on a problem that needed a slightly different structure or path, it just failed. It couldn't adapt because it had essentially memorized a specific solution pattern.
Okay, so the problem is clear. Standard Markovian RL doesn't really provide a strong theoretical reason for useful reflection at test time, and might even incentivize memorizing training solutions instead of flexible thinking.
Right, it optimizes for a known world, essentially, but complex reasoning often feels more like exploring an unknown territory.
Which perfectly sets up their innovation using this Bayes adaptive RL framework, BRL.
Yes, this is the big conceptual shift. Bayes adaptive RL starts from a different place. It doesn't assume the agent knows the task, the environment, the MDP perfectly. Instead, it explicitly models and works with uncertainty about the underlying problem structure, the rules of the game, so to speak.
Uncertainty about the best way forward, or maybe what a correct intermediate step even looks like.
Both potentially. Think about solving a complex math problem, or like the paper suggests, maybe debugging code. You don't always know the single right path from the start. You have hypotheses, you try things, you get feedback. Bayes adaptive RL tries to capture that. It optimizes the expected outcome, but that expectation is averaged over all the ways the problem might be structured that the agent currently considers plausible.
So it's not just about maximizing the immediate reward based on what it thinks it knows for sure.
No, it's about maximizing the reward given the uncertainty. And this naturally means doing two things at once.
Okay, what are those?
One is trying to get rewards based on its current best guess, that's exploitation. But the other is taking actions specifically to gather information and reduce its uncertainty about the true problem structure.
That information gathering part, that sounds like exploration, but with a purpose.
That's exactly what they call it, epistemic exploration, exploring to gain knowledge.
Okay, so now reflective steps, pausing, backtracking, trying something else, they start to make sense in this framework, don't they?
They do. They become principled actions. They're not just random deviations. They are the LLM's way of actively probing the uncertain problem space.
To get more information and refine its understanding of a correct solution path.
That's the core idea. For complex reasoning, the true MDP, the optimal path, isn't given. Reflection is how the model explores hypotheses about that path and updates its beliefs.
And their specific algorithm for LLMs doing this is BARL. How does BARL actually implement this? What's the mechanism?
Okay, so BARL works by maintaining a belief, which is basically a probability distribution over different plausible ways the problem could be solved. They call these MDP hypotheses.
Where did these hypotheses come from initially?
The paper mentions they can be formed from candidate solutions the LLM generates itself, perhaps through some initial chain of thought rollouts. Like it tries a few ways and considers them all potential candidates.
So it generates a few possible plans or solution paths first.
Something like that. Then, when it has to decide on the next reasoning step, it doesn't just evaluate that step based on one assumed best path. It calculates a kind of posterior weighted value. This value is averaged across all the hypotheses it currently believes are plausible.
Weighted by how likely it thinks each hypothesis is.
Yes, partly. The weight depends on a few factors. One is the value of the action within that specific hypothesis, like a standard Q value. Another is the model's current belief or probability that the hypothesis is actually the correct one.
Okay, and here's the crucial part, linked to reflection. There's a term measuring the consistency between the actual feedback, the rewards it's gotten so far in its reasoning process, and the rewards that specific hypothesis would have predicted. So if reality doesn't match what a hypothesis predicted.
That hypothesis gets penalized, its weight goes down if the steps it's taking and the feedback it's getting contradict what one of its candidate solutions expected. BARL effectively says, okay, that hypothesis is looking less likely.
That consistency check is the reflective signal.
Exactly. It drives the process. If the observed outcomes clash with the predictions of a believed-in strategy, that strategy gets downweighted or even eliminated.
Which then forces the model to reconsider, maybe switch focus to a different hypothesis, a different strategy.
Yes, it leads to hypothesis elimination and strategy switching, as the paper calls it, and it happens precisely because of the detected mismatch. This gives principled guidance on when and why to reflect or change tack. It's not just random flailing, it's belief updating based on evidence.
Okay, let's tie this back to the why, how when using BARL. Why reflect?
To reduce uncertainty about the actual problem structure, which helps it generalize better and perform well at test time on new problems.
How does it reflect?
By maintaining these beliefs over possible solution strategies, checking them against incoming feedback, and eliminating or downweighting the ones that don't match reality.
And when does it reflect?
When that feedback, the observed result of its reasoning steps, contradicts its current beliefs about plausible strategies. That inconsistency triggers the adaptation.
That feels much more solid, much more grounded academically than just hoping reflection emerges from standard training.
It connects the behavior directly to the goal of optimizing performance under uncertainty.
This makes a lot of sense conceptually. So let's talk evidence. Did they show this BRL approach actually works better in practice?
They do. They ran several experiments. They started with a really neat didactic example, simple but illustrative.
The repeat the prompt token 3 times task you mentioned earlier.
That's the one. Super simple goal. See a token, say 0, output 000, see 1, output 111, train on those.
Standard RL learns that easily.
Yep, learn 00 for 0, 111 for 1, but then you test it with a new token, 2.
And the standard model fails.
Fails completely. It just outputs 00000 because that's what it memorized, worked in training. It has no mechanism to figure out the rule.
But BARL.
BAR, starting with uncertainty, maybe 000000111 222 are all hypotheses, tries a step, say outputting 0, gets no reward, uses that feedback.
The consistency check kicks in.
Right. The 1,000 hypothesis becomes less likely because the feedback contradicts it for the 2 prompt. It updates its beliefs, eliminates inconsistent hypotheses, maybe tries outputting 2, gets feedback. Eventually, it converges on the 222 strategy because that's the one consistent with the feedback for this new token.
It learns the pattern or the adaptation strategy, not just the specific answers it saw in training.
Exactly. It learns how to use feedback to switch strategies and find the right rule. That simple example really clarifies the advantage. It's learning to adapt.
Okay, that's a compelling illustration. What about more complex tasks? They tested on math problems, right?
They did. Standard math benchmarks like GSMAK, MAS, even harder ones like college math and Olympiad bench.
And how did BARL do there?
Consistently better accuracy compared to the Markovian baselines like GRPO and another one they call Progress. And importantly, the improvements were often larger on the harder benchmarks.
Suggesting that this adaptive exploration becomes even more valuable when the problems get really tricky.
That seems to be the implication, yes. When the path is less obvious, being able to effectively explore and adapt matters more.
You mentioned efficiency gains earlier too, fewer tokens.
Yes, significantly fewer. BARL generally achieved its higher accuracy using considerably less computation, fewer tokens generated. The paper reported some really big numbers like up to 39%, 50%, even over 90% reduction in token usage on some setups compared to baselines, while still getting better answers.
Wow, better accuracy and much cheaper to run. That's huge for practical use.
It really is, and they dug deeper to understand why it was working better. They did some ablation studies.
What did those show?
Well, one interesting finding was that just reflecting more often doesn't automatically mean better performance.
So frequency isn't the key.
Apparently not. Some baseline models might backtrack a lot, but still end up with the wrong answer. It seems BRL's advantage comes from more effective reflection. The thinking steps it takes are more valuable.
How did they measure effectiveness?
They used a metric related to the Bayesian framework, the state action values, which capture not just the immediate reward potential, but also the value of the information gained by taking an action. BNRL's actions consistently had higher Bayesian values.
So its exploration steps were better chosen, more likely to reduce uncertainty or lead towards the right path.
That's the idea. The steps are guided by the goal of reducing uncertainty effectively, not just exploring randomly. It ties right back to the Bayes adaptive principle.
And they confirmed the memorization issue with standard RL too.
Yeah, that length-controlled GRPO experiment really drove it home. It showed standard RL can learn minimal length, non-reflective policies that look good on training data by essentially memorizing, but those brittle policies then fail to generalize. It supports the whole theoretical argument against relying on Markovian RL for robust adaptive reasoning.
Okay, the picture seems quite clear then. BRL isn't just a minor adjustment, it's using a fundamentally different optimization approach.
Right, an approach that directly optimizes for navigating uncertainty and adapting based on feedback, that seems much better aligned with what complex reasoning actually requires.
So the key takeaway is that BRL offers this principled method for enabling effective reflection, optimizing for test time generalization through belief updates and strategy switching, leading to better accuracy and efficiency.
Compared to standard methods that might just memorize training solutions and lack that adaptive capability when faced with novelty.
And the authors see this applying beyond math problems.
Definitely. The source mentions extending BRL to other domains. Coding seems like a natural fit with debugging and trying different approaches.
And maybe general to genic tasks too, where an AI agent interacts with a complex world.
Exactly. Anywhere the rules aren't perfectly known up front, or where the agent needs to adapt its plans based on interactions and feedback, this framework seems broadly applicable.
It feels like a really promising direction for building more flexible and robust AI reasoners.
I think so too.
All right, so we started with this puzzle. How do we get LLMs to genuinely reflect and adapt, beyond just hoping it happens? We dove into why standard RL might not be the best tool for the job, and then explored this innovative Bayes adaptive RL framework and the BARL algorithm as a principled solution.
And the core idea that emerged is pretty powerful, isn't it? That improving reasoning isn't just about reflecting more, but reflecting more effectively, treating the problem like navigating an uncertain environment, actively gathering information, and updating your strategy based on what you learn.
It really shifts the perspective. So here's a final thought for you, our listener, to maybe chew on. If this ability to handle uncertainty and adapt strategies based on feedback is key to better LLM reasoning, what other human-like problem-solving skills could we potentially model by thinking about LLMs as agents navigating uncertainty?
Yeah, what does this imply for the kinds of tasks we might set for them, or how we should even evaluate their intelligence in the future?
Is it just about final answers or more about the process of discovery and adaptation?
It definitely opens up some interesting questions about the future of AI reasoning.
Indeed. Thanks for joining us for this deep dive. We hope it gave you some food for thought.